Well, what happens with real gases? In an ideal gas, there's no attractions between gas particles. Well, real gases do have some attractions between the particles. In an ideal gas, the particle volume is negligible. But gas particles do have volume, and under some conditions, that does become significant. Real gases act much like ideal gases at standard temperature and pressure. It's when we get to extremes of very low temperature or very high pressure where the behavior differs. So if we look at the molar volumes of an ideal gas, it's going to be 22.41. And we compare chlorine, carbon dioxide, ammonia, nitrogen, helium, and hydrogen, all real gases, actual measurements. Their molar volumes are very close to that of an ideal gas. And we see that helium and hydrogen and ammonia, well, actually all of these guys at the end, very, very close. Carbon dioxide and chlorine are a little bit off. Well, what's the effect of the actual volume of gas particles? When we get to very low pressures, the molar volume of argon nearly identical to that of an ideal gas. Because at low pressures, the particles are very far apart. But as we increase the pressure, by decreasing the volume of this container and we're squeezing these particles together, now the size of the particles begins to matter. You take the people of Wyoming and you start to condense them, bring them into maybe a really big football stadium, and now the size of the people starts to matter, whether they're little tiny skinny people or they're big giant people, right? The size of them starts to matter when the pressure gets high because they're getting closer together. And so then what happens is the actual volume of the gas is larger than predicted because the particles' volume does make a difference. So what we see here is if we look at the molar volume versus pressure, as the pressure increases, there is a noticeable difference between the argon and the ideal gas. The argon's pressure is going to be larger. At low pressures, they're the same. These are very high pressures. 200 atmospheres, that's a lot of pressure. That takes a specialized container to hold that kind of pressure. Well, back in 1873, Johann van der Waals modified the ideal gas equation to fit the behavior of real gases. Now, most of the time we're not doing work that's detailed enough to care about this, but there are circumstances where you do need to take into account the fact that you're dealing with a real gas. So he came up with a tweak to the equation. So he said, well, the volume is nRT over P, but at high pressures, it's actually larger for real gases. And so we need to add NB to this volume. N is the number of moles of the gas, and B is a constant called the van der Waals constant, and it's going to be different for each gas because each gas has different sized molecules. So if you're dealing with a specific gas, you can use this correction factor so that you can predict what the volume of the gas would be at high pressure. What the heck? Oh, high temperature. So at high temperature, the pressure of gases is nearly identical to ideal gas predictions, but at low temperatures, it doesn't agree. What happens at low temperatures is that the particles are moving more slowly. And so when they collide with the walls of the container, when they collide with each other, there are some interactions between the particles. And at these lower velocities, at the low temperatures, those can become significant. So for xenon, we see as we get down, so here's room temperature, right, 373, and a pressure of 30 atmospheres. That's pretty high. But we see a little bit of difference between the ideal gas and the xenon. And as we go to lower and lower temperatures, the difference increases because the interactions between xenon molecules, atoms, have more time to happen. So there's another variation to account for intermolecular attractions. It's van der Waals constant A times the moles of gas divided by the volume, that quantity squared. And that is subtracted from the predicted pressure. So we need to go over the van der Waals corrections to the ideal gas law, but the book has no examples of problems with them. And so it's going to end up being sort of a conceptual question on an exam. It's in the course outline, so we have to talk about it. So you can put those two corrections together, and you come up with this mess. Correction for intermolecular forces, correction for particle volume. And people have measured these constants for different gases, and so if you need them, you can go look them up in a table. If we plot PV over nRT, what would that equal? What's equal to PV over nRT? Number of moles. That would be moles of gas. If we plot that versus pressure, for an ideal gas, we would expect that it would be a constant line, a straight line here, horizontal line. N equals PV over RT is going to be a line. But we see different behaviors for real gases. Helium gas shows a straight line, but with a high slope. Water goes way down and then starts to come back up at higher pressures. So we get these curves. When we have a curve that's lower than the ideal, that tells us that the important factor is the intermolecular attractions. A gas with intermolecular attractions is going to take up less volume. If we see higher, then we see that molecular volume is the most important. We haven't talked about this in class yet, but helium atoms have very little interaction with each other. We'll talk about intermolecular forces later. Intermolecular forces between helium atoms are almost non-existent, but the volume is a factor. Volume is a factor, but the intermolecular forces that attract water molecules to each other are much more significant, and that's why we see this dipping below the line. And that's the end. Thank goodness.